Alright, in this video we are going to help prepare you for the AP Statistics test by talking about experimental design. Sorry, but this video is going to be a little bit longer than the others because there is a lot of content here. It's not very difficult, but there's a lot of content to talk about. So what are you going to need to know for the AP Statistics test? First, you're going to need to know the four major aspects of a good design of an experiment. You're going to need to know the three different types of designs. You're going to need to know how to make an experiment truly random. You have to recognize good and bad designs, and you could recognize my spelling mistake there. I do make a lot of those, sorry. And you need to know all the little teeny tiny aspects that make an experiment good. So let's start making sure we understand why we need experiments. First, you're always trying to answer a research question. A research question is something like, does an explanatory variable cause a change in response variable? Like, does a new teaching strategy cause better grades for students? So the explanatory variable is some new type of teaching method, and the response variable that we're trying to change is students' grades. It could even be something like, does watching violent TV shows cause children to be more violent in the real world? Again, these are research questions that we're trying to answer. There's always an explanatory variable and a response variable. Now, we can answer a research question with one of two things: an observational study. In an observational study, you as the researcher do nothing but just observe. So you might sit and watch a teacher who uses a new teaching method, and you observe what the grades of those students are. And then maybe you observe another teacher using a more traditional lecture style format, and you observe what those students' grades are. But you're not doing anything. You're just observing. You didn't pick the groups. You didn't tell them what to do. You just observed. Now, through observational studies, you can certainly show if there's an association between two variables. You could even show a strong relationship between two variables. But unfortunately, you cannot show a causal relationship. Now, I didn't say casual, I said causal. A causal relationship is one where you show a cause and effect relationship, where X will cause Y to change. And the only way you could show a true cause and effect relationship is with an experiment. Now, an experiment, you as the researcher have all the control in the world, which is why an experiment is the only way to do it. Every year, I almost see an AP Stats multiple choice question that says, what's the biggest difference between an observational study and an experiment? And the number one answer is that in an experiment, you have that direct control to show a cause and effect relationship. When an observational study, you do not. All right, let's talk about the four main aspects of all good experiments. The first main aspect that every good experiment must have is comparison. What we mean here is that you always, at the very least, must have two groups. At the very least. You can't have everybody doing the same thing. If everybody does the same thing, how do you know if what you're doing is making a difference if you have nothing to compare it to? So at the very least, you must have two groups. Now, one of those groups could be a control group that gets nothing, or that control group maybe is taking a placebo, which we should all know is basically a fake pill that does nothing. But regardless, you got to have two groups. Now, do you need a control group? No. If I simply wanted to know what makes pain go away faster, medication A or medication B, well, half of my people get medication A, half of my people get medication B. That's going to help answer that question. I don't have to have a group that gets nothing. I could have another group, group C, that gets a placebo, but I don't have to. Now, if all I want to know, does medication A work? Well, then yes, I have to have another group to compare it to, which in that case could be a group C that gets nothing, a control group that gets a placebo. But the point I'm trying to make is that if any good experiment, you got to have at least two groups to compare. All right, randomization is the next part that must be in every good experiment. Randomization deals with how you determine which subjects get which treatments. For example, if I have 300 people all ready to go for my experiment here to determine which is better at relieving pain, medication A, medication B, and then I'm even going to throw a control group in there. Okay, how do I determine who gets what? It's got to be done randomly. The easiest way to do this, especially, I know you're going to be asked of this on a test. The easiest way to do this is just give everybody a number, 001 through 100. I'm sorry, 300. So everybody gets a number, 001 through 300. And then I could use a computer number generator, or I can use a random number table that I found on the internet or something, and I could randomly get numbers. So the first 100 random numbers selected will go into group A. The next 100 random numbers will go into group B, and the remaining 100 random numbers will go into group C. That is how I could do it randomly. But it has to be random. At no point can you select, oh, here's Steve. Steve's going to go into group A. Why? I don't know. I like Steve. No. It's got to be because Steve was randomly chosen to go into group A. All right. Replication. What is replication? Replication is the idea that bigger groups means better evidence. If I really want to show that medication A is better at medication B or nothing, group C, I want to have a lot of people. If all I do is put one person into group A, one person into group B, and one person into group C, there's no replication. Because one person can have their pain go away for a million other reasons besides because they're taking medication A, as opposed to one person who took medication B. So replication is more people, right? I mean, using 100 people. If I could show you that 100 people all on medication A had their pain go away faster than 100 people on medication B, then I think I've proven that medication A was better. Want more replication? Make it 1,000 people in every group. Want more replication? Make it 10,000 people in each group. That's replication. Now, there is a second meaning to replication, which can mean literally just doing your experiment again and again and again and again. Start from scratch and do the whole experiment again with another 300 people, another 300 people. Because if you can continue to show from one experiment to the other that medication A always comes out on top, well, boy, you have more evidence that medication A is better. All right, the last major aspect is really important, and this is control. Now, I want to emphasize that this is not control group. Remember, we already talked about a control group that can be used for comparison if needed. Control is talking about the idea that if you have, let's just go back to 100 for a second. If you have 100 people in all three groups, you want those three groups to be as similar as possible. I want these 100 people, these 100 people, and these 100 people to all be as similar as possible. The only difference I want them is what medication they're taking, A, B, or the placebo C. Now, we call this control because as the researcher, I'm the one that's in control of this. So for example, if I have the 100 people in group A, I mean, some of them got knee pain, some of them got ankle pain, some of them got pain in their hands, some of them got pain in their legs, some of them got headaches. The pain's all over the place. Well, boy, man, that could be tough, right? So here's the deal. Maybe I use all people with headaches. That way, everybody has headaches. All 300 people all have headaches. That way, I could truly pinpoint that my medication is going to help your headache go away faster. Now, if I want the medication to be used for any pain, well then maybe it would be a good idea to have a nice mix in this group. But the problem with this is if this group right here has knee pain, joint pain, hip pain, leg pain, arm pain, shoulder pain, then this group needs to have all different kinds of pain, and this group needs to have all different kinds of pain. The point is you want to make these groups very, very similar. Now, how much medication do they take? Ooh, boy, I want to control that because if medication A is taking 50 milligrams and medication B is only 20 milligrams, well, then now I got a confounding variable. Maybe people in medication B got better not because of the medication, they just took more of it. They took a larger milligram sample. So I can control that. No matter what group you're in, you're taking a 50 milligram pill. Well, except for the placebo, who I know takes no pill. By the way, using a placebo is a form of control because when you're working with human beings, that's when we establish the placebo effect. So let's talk about that real quick. The placebo effect is when a human being knows they're taking something. That knowledge of taking something alone might cause a response to change. Whether that something is literally impactful or not, the moment that I know I'm in an experiment, the intention of the experiment itself might cause a change. Versus if I'm told, oh, thanks for participating, but you're going to go home with nothing. Well, then that might make me actually have more pain because I'm so upset that I'm going home with nothing. So the point is, you can control for the placebo effect by giving everybody something. So it's important to understand that the placebo effect is actually impossible to get rid of. What you do is you control for it by allowing everybody to at least think they're taking something. Whether it's something real or not, everybody thinks they're taking something. That is showing control. What time of day should you take the medicine? Well, everybody take it at 7 a.m. with a full glass of water. That is control. All right, so any way that you can keep everything this similar as possible, that is establishing control. You should try to have as much control as possible in an experiment. All right, what are some other aspects of an experiment? Well, we already talked about using a placebo to help control for the placebo effect. I get a lot of kids that try to say that they can eliminate the placebo effect. That's actually impossible. You cannot eliminate the placebo effect, but you can make everybody think they're taking something by giving out a placebo. We already talked about using a control group. A control group is smart to use because it gives you something to compare to. If I have a new medication that's supposed to help lower my blood pressure, well, I should probably have a group that doesn't get it to compare to just to make sure that the blood pressure truly went down. I mean, if everybody gets the blood pressure medication, how do I know that the blood pressure went down if I don't have something to compare it to? So a control group is kind of like a baseline group. It gives you something to compare to. But remember, it's not a necessity. Okay? If you're just looking at medication A versus medication B, maybe you don't need a control group. All right, single blind means that the subjects do not know what they're taking. When you're working with human beings, you should blind them. With the pill, you can give a placebo to single blind. Now, if I'm going to go back to an example I mentioned earlier, a teaching method used to help improve student performance. Well, if I'm a student, I'm going to know if I'm being taught with a standard lecture style format or if I'm being taught with some cool new hands-on approach. So in that situation, you can't blind me because I'm going to know what's happening. It's like if I said, hey, are flashcards or a computer better at helping you learn multiplication? Well, I'm going to know if I'm using flashcards or if I'm using a computer. You can't blind me to that. So sometimes you cannot blind your subjects, but you should if possible. Working with animals or objects that are not humans, you obviously don't need to worry about blinding. Now, double blinding means that you're not only blinding the subjects, but you're also blinding the evaluators. See, in any experiment, somebody at the end has to measure the response, whether it's grading papers to see who has actually learned more in a class setting, or maybe it's asking people, hey, how's your pain? Is your pain better? Is it worse? How long did it take your pain to go away? Whoever's going to actually analyze that should be blinded. That way they don't know what they took. They're just answering the questions, doing the measuring of the response variable without knowing. That should happen if possible. Lastly is the treatments, and anybody know another spelling error? The treatments you have to understand are what you're giving out. Okay? What you're giving out to the different groups are your treatments. And a lot of times AP test questions will simply ask you to list treatments. So make sure you know how to do that as well. The only time that can be tricky is if you have multiple variables. Like let's say that you're working with grass and you're trying to grow grass and you know grass needs water either once a day, twice a day, or 3 times a day. And you know that grass needs fertilizer, but you're trying to figure out which fertilizer is better, A or B. So now you have 3 different watering levels, 1 time a day, 2 times a day, 3 times a day, and you got 2 different fertilizers, maybe fertilizer A and fertilizer B. That's actually going to create 6 groups because you got A once a day, A twice a day, A 3 times a day, B once a day, B twice a day, B 3 times a day. Sorry for the confusion there, very ugly picture, but you get the idea that there's actually 6 different treatments given out. All right. Now let's talk about the different ways to design an experiment. All right, there are 3 very good, very acceptable designs. Number 1 is what we call a completely randomized design. Here, groups are created completely randomly. So, sorry for the typo, you're trusting that randomness will make the groups as similar as possible. I make a lot of spelling errors. This program I use does not have spell checker. So when I type super fast to try to get things done quick, I end up with a lot of typing errors. Sorry about that. And it doesn't allow you to go back in and edit those mistakes. That's why I kind of end up just leaving them. All right, so anyway, completely randomized design. When you go ahead and make your groups, right? Group A, Group B, Group C, you're completely allowing randomization to evenly disperse all variables into those groups. So if I'm trying to, again, go back to my pain medication, medication A, medication B, and the placebo C, I'm going to have to trust that randomization will put old and young people into all three groups, boys and girls into all three groups. Different pain into all three groups. Maybe some people have severe pain at the beginning and some people just have a little bit of pain. So pain severity, I need that to be evenly dispersed into all three groups because I want these three groups to all be as similar as possible. In a completely randomized design, I'm just going to trust that randomization will do that for me. To be honest, if you remember what we've learned about probability, the probability that all the old people get put into group C is pretty unlikely, which is why we don't consider or worry about it happening if we're going to use a complete randomized design. Easiest way to do this is to give everybody a number, 0, 1 through 300. Pick out 100 random numbers using a random number generator. They go to group A. Next 100 pick go to group B. The remaining go to group C. All right, a randomized block design. Here you're going to first separate your subjects by a common variable. Then you're going to run a separate experiment within each block. So a randomized block design is helped to control for a confounding variable. If you can think of one variable that will definitely have an impact on pain relief, then you're going to want to block on it. And you have to make that decision about what that one variable is. For example, maybe you think it's age. Okay, so I'm first going to block on age. I'm going to take my 300 subjects and based on age, I'm going to separate them. The young people are going to go into the one group, maybe that's 18 to 40. The middle-aged people are going to go into another group, maybe that's 40 to 60. And the elderly are going to go into another group, that is 60 and older. Sorry if I offended anybody by calling you elderly if you're over 60. Hopefully nobody over 60 is watching this video. But anyway, now that was not random, that was all done on purpose. Now, you might not have exactly the even amount of all of these, like maybe you have 100 young people, maybe you only have 50 elderly people, and maybe you got 150 people in the middle age. Okay, great, who cares? Now, then you're going to run a separate experiment within each group. So of the 100 young people, you're going to give 1/3 of them treatment A, 1/3 treatment B, 1/3 treatment C. So maybe 33, 33, 34. How am I going to do that? Of course, randomly. Everybody gets a number, 0, 0, 1 through 100. The first 33 go into group A, the remaining 33 go into group B, and then the leftover 34 go into group C. So I'm running my own little experiment on the young people. And then I'm going to do the exact same thing on the 150 middle-aged people. Randomly choose 1/3 of them to get A, 1/3 of them to get B, 1/3 of them to get C. So 50, 50, 50, chosen randomly. And then of the elderly, same thing. 1/3, 1/3, 1/3, A, B, and C. So the point here is now I can clearly see if everybody taking medication A got better, well then it appears that age doesn't matter because the young people got better, the old people got better, and the middle-aged people got better. So blocking really allows me to reduce the variation within my groups because now instead of having it be all mixed up, well, I'm purposely making sure that the young, middle, and elderly are all getting the treatment. See, if we go back to completely randomized, well, you know, we hope that every group has old, young, and middle-aged, but you never know. Maybe group A has no young people in it. I mean, it could happen, right? All the young people go into group B and group C, so at the end, nobody that's young took medication A. That could be a problem. That could become a confounding variable. Now, you could only pick one variable to block on. So you got to make a choice. Maybe somebody else decides to block on where the pain is at. We got head pain, knee pain, shoulder pain. Okay, and then the list can go on. You can make as many blocks as you want. There's no restraint to how many blocks you could create. But once you have these blocks, you must give out all treatments within each block. So everybody with head pain, you're going to get into a group. Some of you get A, some of you get B, some of you get C randomly, of course. Everybody with knee pain. Some get A, some get B, some get C. That's how you do a randomized block design. All right, the last design is called a matched pair design. Here, you could pair the subjects together based on many similarities. Now, the only issue here is you can only have 2 treatments. So if I'm going to do this example, I have to eliminate treatment C and only go with medication A versus medication B. Obviously, some people say, well, can't you just make triplets? Well, sorry, no. We work with pairs, not triplets. All right, so when we pair people together, we want those 2 people to be extremely similar. We want to pair together 2 guys who are of the same age, who have the same pain in their knee, whose severity is the same. We want these 2 guys to be very similar. Then guess what? One of them randomly gets A, one of them randomly gets B. And then we create another pair, maybe 2 girls that are both elderly. They both have pain in their hands. And then again, one of them gets A, one of them gets B. So you create pairs that are very, very similar for many reasons. And then one of them randomly gets A and one of them randomly gets B. So you're still having the randomness in there in terms of who gets what, but you're really having a lot of control here. Because now, if you can truly show me that the person taking medication A got better, well then you can't say it's because, well, they were girls. No, they were both girls. Well, they had knee pain and they had shoulder pain. No, they both had hand pain. Well, one of them was really old and one of them was really young. No, they were both really old. See, the point is that if I just let it be completely random, then, what if all the young people do get put into group B? Well, then all of a sudden, maybe they got better because they were young. It had nothing to do with medication B. They were just young. See, that's a confounding variable. So I'm not saying completely randomized design is bad. In fact, most experiments are done completely randomized. But block and matched pair just allow you to take it a little bit further. Now, the last thing I want to say is technically a matched pair design is an advanced form of blocking. It's when you create blocks of size 2 that are very similar for many reasons. That is a matched pair design. So it is a form of blocking. All right, what else can we talk about here? I already kind of mentioned this. I just want to go over it again because this does come up on the AP test. What is an advantage of block design? Allows you to reduce the variation within your groups to better focus on the explanatory variable and its effect. If in group A, I got old people, young people, knee pain, shoulder pain, head pain, leg pain, ankle pain, well then all of a sudden, my results could be a little bit clouded. But if I make all of those people, right, if I create groups, blocks, where, okay, all of these people are old. They're all old. So I'm reducing the variation. I'm making them all old, and then I'm handing out all the treatments. So I could really see how do these treatments affect old people. So I'm really honing in on what I'm trying to look at. But then again, I'm going to have another block for young and another block for middle-aged as well. The AP loves asking questions about how to select a variable to block on. Just make sure you select the one variable that has the greatest effect on your response variable. I remember a question where they were trying to use a new medication versus an old medication to help dogs with hip and joint pain. And they said, do you want to block on the breed of dog or block on their vet that they go to? Well, the smart choice there is to block on breed of dog because Dalmatians might have very different amounts of hip and joint pain as opposed to some little tiny Chihuahua. Whereas the vet, all different kinds of dogs go to each vet. I mean, what vet you go to has nothing to do with your pain in your joint or your hips. Whereas the breed of dog, sometimes smaller dogs do have more hip and joint pain, or maybe larger dogs do. So blocking on breed of dog would be a much better decision. So I'm going to get a whole bunch of golden retrievers together. Half of them get the new medication, half of them get the old. That way I can really focus on how does that medication affect golden retrievers. Then I'm going to get a whole bunch of Chihuahuas together. Half get the old medication, half get the new. That way I could really focus on how that medication affects Chihuahuas. Whereas if you just go to the different veterinarian clinics, well, at a veterinarian clinic, you're going to have all different types of dogs. That's not going to work. So they love asking you that question. The key thing is you're trying to eliminate a confounding variable from becoming confounding. All right, now another thing that comes up a lot of times on the AP test is whom can you conclude your results to? So when you're done with an experiment, can you say that, hey, wow, this new drug works for all people? Well, no. Your conclusion could only be applied to the population your samples came from. So if you randomly take a group of people from Montana that are aged 35 to 40, well, then you can only apply your results to people from Montana who are aged 35 to 40, because that's where you got it from. Now, the other problem is if you ask for volunteers to do your experiment, well, then you cannot conclude the results are true for everyone. You can only show a cause and effect relationship for those people. So, if I ask for volunteers, well, then all of a sudden, that's actually a confounding variable, because maybe you got better because you volunteered and you cared to get better. Well, I could still show a cause and effect relationship. I could still say that A causes B with a good experiment. But if I use volunteers, it makes it really hard to apply your results to all people. So the problem is that, if you really want to do a good experiment, you have to collect a random sample from all around the world. And those people have to be willing to do it, which is another problem. And then you have to conduct the experiment. Then you could say that it's a true cause and effect relationship for everybody around the world. So usually experiments are really precise. They're only for small groups of people that they're focusing on. All right, now, the good thing about experimental design is typically these are the easiest multiple choice questions that cover basic ideas of a good experiment, or they may have you select best way to conduct an experiment. So you got to read a lot here, but a lot of times these questions could be answered if you just use a little bit of common sense. Honestly, just use common sense and think about what's the best way to conduct an experiment. Typically, FRQ questions will almost always ask your best way to create a roughly equivalent groups. They want to make sure that you know how to create groups. Whether it's completely randomized, block, or matched pair, you need to explain how to create a good group. And remember, first and foremost, it's got to be done randomly. These are very easy questions. All right, what I want to do is just quickly end with a really rough example here. So a teacher wonders what works better at increasing understanding on a geometry test. Sorry, I forgot the word test there. A new hands-on approach to teaching or a standard lecture style. Design an experiment. So the explanatory variable is teaching style. It comes in two treatments, the new hands-on approach and a standard lecture style. To design an experiment to see how it affects the response variable, the score or your understanding of geometry, which we could test and we can measure with a geometry test. Well, if I want to do a completely randomized design, maybe I go and get 200 students, randomly select 100 of them to get the new hands-on approach, randomly select 100 of them to get the standard lecture approach. They should all be taught at the same time, because time of day that you learn math might impact how well you understand it. What about boys and girls? Because gender could have an impact. Well, I'm just going to have to trust the randomization, put boys and girls into both groups. What about previous knowledge about geometry? Well, once again, I'm just going to trust that your previous knowledge of geometry is evenly dispersed into both groups. So there's some people in both groups that already know a little bit about geometry, and there's also some people in both groups who know nothing about geometry. Now, if I want to do a block design, well, then maybe I'm going to say, wait a minute, oh boy, boys and girls, definitely. Gender is definitely a confounding variable, because boys mess around a lot and they don't pay attention where girls do. So, okay, I'm going to block based on gender. So I'm going to select boys and girls here. Now, of the boys, half of them are going to get the hands-on approach. Half of them are going to get the lecture. This is guaranteeing that boys go into both groups. And same thing with the girls. Hands-on approach and lecture. Okay? So blocking is just trying to reduce that variation, because again, there's always that what if. What if all 100 kids in this group are boys? I mean, I doubt that will happen, but you never know. And if that does happen, we have a huge confounding variable. Lastly, I can design a matched pair design where I pair people together for a lot of similarities. So I'm going to pair Emily and Joanne together. They're both girls. They both are very smart. They both have very high IQs, and they are very good math students. Then one of them gets the hands-on lecture, one of them, or the hands-on approach, one of them gets the old standard lecture style. Then I have another group. Maybe it's Tommy and Jimmy, and they both are very low achieving students. They both are very bad at math. They are both boys. They both are roughly the same age. Okay, so they're very similar. One of them randomly gets the lecture, one of them gets the hands-on approach. So great ideas here to design a different experiment based on a completely randomized design, a block design, or even a matched pair design. But the key thing is it's got to be done randomly. So regardless of what step you choose, there's got to be that aspect of randomness. So who gets what? Well, okay, if I'm going to go to completely randomized design, everybody gets a number, 001 through 200. The first 100 numbers selected go into the hands-on group. The other 100 get the lecture style. If I'm going to block on boys and girls, okay, let's say I end up with, 75 boys. Okay, every boy gets a number, 01 through 75. The first half that I pick get the hands-on, the remaining half get the lecture. They don't have to be equal. Obviously, you can't split up 75 in two equally, so one group has one more kid than the other. What are you going to do? And then I would do the same thing with the 125 girls. The point is, that's how you make it random. It's got to be random at all times. All right, guys, so hopefully this was a quick video just to really give you a quick remembrance of how to do all this experiment stuff. The key thing, honestly, to worry about is that these questions are really easy. They can oftentimes be answered with just a little bit of common sense, but sometimes hearing these concepts again will definitely help jog your memory so that you can do well on the test.